Mean value theorem. We've got the formula, not the formula, but kind of the definition up there. If we have f is continuous on a closed interval, differentiable on an open interval, then there exists a number c such that our derivative, I want you to write this down here. This is our instantaneous rate of change, or IROC is what I'm going to abbreviate it as. That's our instantaneous or our slope. On the right-hand side, that is my average rate of change, or AROC, average rate of change. We're finding at what c value is that slope of that line going to be the same as my average rate of change. Okay, so we've got a picture over here that's going to help us kind of figure out what these things are from. So in this figure on the right, label the indicated ordered pairs. So I've got a point at A. So if I was labeling this point, this would be the point A, f of A. And this would be the point B, f of B. Next thing it says is to label a segment whose length is f of b minus f of a. If I was trying to label a segment that is f of b minus f of a, would that be a vertical line or a horizontal line? If I'm looking at the difference between the y values. Difference between the y values would be a vertical line here. That is our change of y values, or that's our f of b minus f of a. Okay, next one says to label a segment whose length is b minus a. So that would be a horizontal distance between a and b. And then if we found the quotient of this whole thing, the quotient of that whole thing is actually just our slope formula. Okay, that's the slope of the segments joining the 2 points of a, f of a, and b, f of b. Okay, so let's draw that line in there as well. Okay, so we're going to kind of go out of order here. On part 6 there, it says, on the graph above, locate the c value that is guaranteed by the mean value theorem and draw a line tangent to the curve at c. So if I'm looking at this this graph here, if I were looking at this and putting my pencil on that, at what point does it become tangent to that parallel line?
Wait, which one's the parallel? Like there?
Yeah, about right here, right? So at this point, right about here, we'll label that my c value. And this line is tangent, which makes it parallel. That's not exactly perfect, but you get the idea. So f prime of c, that gives the slope of our tangent line. To the curve f of x at the point. How would I label that point right there? C, f of c. Okay, so those two lines that we have on our graph, those two lines are related how? They are parallel to each other. Okay, so therefore, using our mean value theorem, there is two parallel lines through the points. First A, f of A, and B, f of B. And then the other tangent to the curve f of x at the point C, f of C. Okay, so if it is a continuous and a differentiable function, there must exist a point C in between those 2 points of A and B on your interval that is going to be parallel to your average rate of change. That's what the mean value theorem says. Okay, any questions on that? Okay, let's look at an example then on the next page. So I've been given a graph on the right hand side of this function. F of x is equal to 3 minus 5 over x on the interval from 1 to 5. Okay, state why or why not the theorem applies, and if the theorem does not apply, or sorry, if it does apply, find the value that is guaranteed by the theorem. So first of all, if I'm just looking at this picture, okay, from 1 to 5, so at 1, my value is here, and at 5, my value is here, right? So the average rate of change is the line that is in between both of those things. At what point, or what x value approximately, if I drew a tangent line through it, would it be parallel to that blue line? Approximately. Maybe like 2.5-ish, so like maybe like something like right here. If I were to draw a tangent line there. Okay, so that value, that c value, is what we're going to find algebraically. Okay. But we have to state our conditions first. Our first condition is that the function is continuous. Is this function, that first function in blue, continuous on the interval from a to b? Yes. So first condition is that it is continuous on the interval a to b. Okay, next condition is that it is differentiable. So it's differentiable on the interval a, but it's not a closed bracket on this one, from a to b. The third thing that we need to show is that the instantaneous rate of change is equal to the average rate of change, and that will give us our c value when we do that, okay? So instantaneous rate of change, that's my derivative of my function. So I need to take the derivative of my function. So f prime of x is equal to, so taking the derivative of this up here, I could rewrite that as negative 5x to the negative 1. So my derivative would be positive 5x to the negative second, or 5 over x squared. Yes? So that is my instantaneous rate of change. That's my slope for any point on this curve if I plugged in the x value. But what I need to do now is I need to figure out what is the average rate of change. How do I find the average rate of change of this blue line here? Set them equal to each other. That's what we will do afterwards. But how do I find average rate of change? Average rate of change is another word for slope, right? So yeah, we're going to use our slope formula. Slope formula is just f of b minus f of a over b minus a. So in this case, we're actually looking at f of specifically 5 minus f of 1 all divided by 5 minus 1. That's what we need to evaluate. So I'm plugging in 5 and I'm plugging in 1 into my original function there. So I've got 3 minus 5 over 5 minus 3 minus 5 over 1. That's all divided by 4. Okay, if we simplify that, I get 3 minus 1. So that would give me 2. So 2 minus, and then 3 minus 5 gives me a negative 2. So this would end up equaling positive 1. Okay, so my average rate of change is 1. My instantaneous rate of change is 5 over x squared. I'm trying to find out, well, when are they equal to each other? So let's set them equal to each other. So I've got 5 over x squared is equal to 1. If I cross multiply and solve, I get 5 equals x squared. And then you take the square root of that, you get x equals plus or minus the square root of 5. Okay, and if we go back to kind of what we thought it was going to be, is the square root of 5 close to a little bit more than 2?
Sure.
Yeah, right? Square root of 4 is 2, so square root of 5 is obviously just a little bit more than 2. So our prediction there is correct, and we can go ahead and say that our c value in or on the interval 1 to 5 is the square root of 5 by the mean value theorem. You could also say that like we have to disregard the square root of, all right, totally forgot to talk about that. Why did I disregard the square root of, or the negative square root of 5? Because it's not in my interval, right? So I can only take the numbers that are in my interval, so C would have to be square root of 5 in this case. Okay, next one we've got, it has some trig values in there, so it's going to be okay. We are going to use our calculator to solve this one, okay? So I'm going to show you how to use your calculator to evaluate this. You could actually do this one by hand as well, but I am going to show you how to use your calculator. The other thing to note is that this question is asking us to find the equation of the tangent line. So not just find the point, right, that is going to have a parallel tangent line. It's actually finding the tangent line of that point, okay? So, but first thing that we need to do is we need to find the derivative, okay? So this you have to do by hand. So f prime of x is equal to, what's the derivative of 2x plus sine x plus 1? 2 plus cosine of x. Okay, that's my derivative. Okay. We are looking at the interval from 0 to pi. Okay, so if we look back up here, oh, and I forgot to do it already. The first thing that we need to do is state our conditions. First thing is this function continuous and differentiable? Well, if we look at each of these pieces individually, is 2x and sine of x and 1, are those all differentiable and continuous?
Yeah.
Yes, they are. There's no holes. There's no nothing that's going to like create some sort of maybe like absolute value kind of graph. Think about a cusp or kind of a sharp edge there, okay? So we're looking at when is my average rate of change equal to my instantaneous rate of change. I'm going to write down the conditions though, saying that we checked those. So f of x is continuous on the interval from, in this case, 0 to pi. And f of x is differentiable on the interval not closed but open 0 to pi. Third thing we're checking, when is the instantaneous rate of change equal to average rate of change? Okay, so we're looking at when is this piece, this average rate of change, this 2 plus cosine of x, when is that going to be equal to average rate of change? Now, this is what we're going to find the average rate of change on our calculator, okay? Average rate of change on your calculator, we're going to type this f of x into y1. So on your calculator in y1, I want you to type in 2x plus sine of x plus 1. Okay, once you've typed that in, we're not going to graph it yet. We're going to find the average rate of change. So you're going to go back after you've typed it in, go back to your main screen, and you're going to type in y1 of pi minus y1 of 0, all divided by pi minus 0. Now, two things we got to remember. How do I type a fraction? A fraction is alpha y equals, gives you that fraction. But then how do I type the y1? How do I get that?
Alpha trace.
Alpha trace. Alpha trace allows you to grab that y1 value. Okay? So when you plug that whole thing into the calculator, you should get one number. This number is really not that bad. We get 2. Again, we could have evaluated this by hand without a calculator, but let's say like the average rate of change was like 2.5732, right? I wouldn't be able to solve that with that equal to 2 plus cosine of x, right? So if you can use a calculator, your calculator can pretty much do this for you once we get that value. So we know that the average rate of change is 2, right? And we found that from our calculator, so this is equal to 2. So now if I want to figure out when does 2 plus cosine of x equal 2 on my calculator, what are we going to do?
Subtract 2.
We could subtract 2, but then what do we do? Is there a function that we can plug that into on the calculator? Not the polysmelt. It's not going to do it for you.
When?
if we want to find out when they're equal to each other, don't we just want to find out where they cross?
Sure,
Yeah.
like that.
So what we're going to do, after we've found the average rate of change, now you're going to go back into your y equals, and you're going to delete the y1, okay? And now your y1 should say 2 plus cosine of x. That's going to be your derivative, 2 plus cosine of x. And then I want your y2 to say your average rate of change, which is 2. And let's tell our calculator, what interval am I looking at? I'm looking at a specific interval, 0 to pi. So in window, I want you to change your x minimum to be 0 and your x maximum to be pi. Once you've done both of those things, you can go ahead and hit graph,
Mine says error.
and you should see where they intersect. Okay? Okay, so your graph should look something like this on your calculator, right? And now from here, what you're going to do to find out this intersection point is you are going to type or hit second trace. Or sorry, is it second calculate actually? Second calculate. Is there a calc button on there?
What is second trace? That is.
It is okay, sorry, it is trace. Second trace. And then you will go to intersection. Okay, we want to figure out where are those points crossing at on the graph. Okay. And then you'll get a decimal answer, but that decimal answer is actually pi over 2. So you have your intersection as pi over 2 comma 2 from your graph. Okay. Do we all get that on a calculator? Pi over 2 or, 1.5 something something. Okay. All right, so now that we've got our point, that is the value at which the tangent line is going to be parallel to the average rate of change. But the question asks us to find the equation of the tangent line. So I need to write out the equation of my tangent line. I have my point. My point is pi over 2, but then do I know my y value? Yes, I do know my y value. No, that's not my y value that's not my y value of the function, that's my y value of the derivative. So I need to plug that back into the function here. F of x equals 2x plus sine of x plus 1. So if I plug in pi over 2 there, I would get 2 times pi over 2 plus sine of pi over 2 plus 1. Yes, so this would evaluate to be, because sine of pi over 2 would be 1. So that's pi plus 1 plus 1. So my y value is actually pi plus 2. So I've got a point that's on my function. Okay, plug that back into my f of x value, not my derivative. And then I know my slope. My slope is 2. Okay, so I know my slope is 2 at that point, because that's what we just found, right? And now I can write my equation. So my equation for this tangent line is y minus y1, which is pi plus 2, is equal to my slope of 2 times x minus x1. Okay.
Can you leave like one? I'm never gonna see you again.
All right. With this being said, there is a practice on Schoology for the mean value theorem. You don't have to do it, but maybe you do 1 or 2 problems to see if you can kind of try it out yourself. It's a circuit. There's 4 pages. I'm not expecting you to do it all, but I just put that in there if you got some extra practice. Okay. Last thing is sometimes the mean value theorem does not apply. Okay. The mean value theorem does not apply if things like functions aren't continuous or functions aren't just differentiable. Okay, so if you have things like, sharp turns or some holes in the graph, that kind of stuff, or maybe vertical asymptotes, that's when the mean value theorem does not apply and you can't do anything. So these are all examples of that case. So if I look at example A, I've got 3x minus x minus 3 on the interval from 2 to 5. Well, what does this x minus 3 look like?
A V.
It's absolute value, right? So we're looking at, that's a sharp turn, right? If it's at a sharp turn, then it's not going to be differentiable on that function. So we can just say that f of x is not differentiable at x equals 3. Okay, now what if my interval was actually 4 to 7? Would it be differentiable from 4 to 7?
Yes.
Yes, but I'm looking at the interval that actually includes the value of 3, so I can't do anything with that. Okay, next one here, I've got 2 over x plus 2 on the interval from negative 3 to 1. Does anyone remember what this looks like on the graphing calculator?
It'd be like the two.
It's like the two things. The one goes down and one goes up, right? So something like maybe this and like this. Okay, so anyways, if I looked at the graph, this would look something like this, which means there's going to be a vertical asymptote where? Somewhere at negative 2, because this denominator, if I set that equal to 0, that's where my vertical asymptote is, right? So it is not going to be continuous at that point of x equals negative 2. Is negative 2 in my interval? Yes. So therefore, we cannot use the mean value theorem because g of x is not continuous at x equals negative 2. And last one. If I had h of x equals x to the 2/3 power, this graph, anyone have any idea what this looks like?
Something like this.
Kind of. You're really close.
I don't know how to make it.
I'm not sure what exactly you're trying to do, but I actually kind of call it the bird looking thing because it does basically, it goes like this. Yeah, on your graph.
I got it down.
Yeah, you thought it was upside down, but that's okay. Anyone draw birds like this when they were in elementary school? Yeah. I probably still would draw my birds like this because I can't draw. So at this point would be what? 0. Okay? This point is 0, and 0 is on my interval. So therefore, there is a sharp kind of turn happening there. So it's not differentiable at that point. Okay? So not differentiable at x equals 0. If you weren't sure what that graph looked like, and it was like a non-calculator question, we could take the derivative of this function, and the derivative would be 2/3 x to the negative 2/3 power.
1/3.
Yes. Thank you. And then if I would rewrite this as 2 over 3x to the cube root of x, right? If I look at this function, right, when would my derivative be undefined? Well, when the denominator, wait, why do I have an extra x there? No wonder you guys are looking at me like I'm crazy. It's fine. Okay, back to my question. What makes this function undefined? When my x value equals what? 0. If I plug 0 in there, right? 0 times 3 would give me 0 in the denominator. So therefore, it is undefined at 0, therefore not differentiable at 0. Make sense? So if you don't know what that graph looks like, take the derivative and then decide, can I actually do anything with that, yes or no, okay? So those are some examples of mean value theorem. If you still aren't sure what it means or how to solve things, please come in and see me for some extra help, okay?